A legendary sword could slice silk and shatter steel in the same swing. This was the power of Damascus steel, a medieval mystery that defied explanation for centuries. By the end of this, you will understand how ancient blacksmiths mastered nanotechnology 500 years before we even had the word for it. We will uncover how a simple recipe of earth and fire gave birth to carbon nanotubes within the blade, and why this supreme technology vanished almost completely. What does it mean for a craft to be so advanced that its own creators did not fully understand it? The reputation of a Damascus blade was forged in whispers and witnessed in steel. For a European knight facing a Saracen warrior, the encounter was not just a clash of cultures, but a shocking confrontation with superior technology. Historical accounts from the Crusades describe these swords cutting cleanly through European blades, or even slicing a feather in two as it drifted through the air. The swirling, liquid pattern on the metal was not mere decoration, it was a visual guarantee. To own such a sword was to hold a masterpiece of both art and engineering, a tool so effective it blurred the line between weapon and legend. This lore persisted long after the last true Damascus sword was made. For centuries, the knowledge was considered lost, a ghost of a technique that modern industry could not replicate. The myth grew in the absence of fact, but every element of that myth, from the cutting ability to the iconic pattern, was a clue. It was as if the swords themselves were leaving a message, written in a language of folded metal and secret chemistry, waiting for a future generation to learn how to read it. That chain of knowledge broke forever in the 18th century. The final masters of the craft took their secrets with them, leaving behind a world that could admire the swords but could no longer create them. This is the blacksmith's enigma. For generations, the technique was an oral tradition, a symphony of steps conducted in the heat of the forge and never transcribed into a manual. Traditional swordsmiths from Europe to Japan could hold a Damascus blade, feel its balance, see its beauty, and know it was superior, yet they were utterly baffled by its origin. They were missing the first and most crucial piece of the puzzle, a raw material that seemed almost magical. The journey of a Damascus sword did not begin in Syria, but in the furnaces of southern India and Sri Lanka, with the creation of a unique steel ingot known as Wootz. These Wootz ingots were the essential seed. They had a peculiar, mottled appearance like a stone sprinkled with metallic glitter. Their composition was a specific, almost accidental recipe of iron ore and organic material like wood or leaves, melted together in a small, sealed clay crucible. This process infused the iron with just the right amount of carbon in a very particular form. Think of it not as a standard steel bar, but as a specialized ingredient, like a rare spice that transforms an entire dish. These ingots were then traded along ancient routes, eventually reaching the master smiths in cities like Damascus. They were the canvas upon which the legendary pattern would be drawn. The smiths then began their ritual. They would heat the Wootz ingot to a precise, glowing temperature, never letting it reach a full melt. They would hammer it, fold it, and forge it with a patience that bordered on meditation. The exact number of folds, the specific heat for each hammer blow, the mysterious composition of the quenching fluid, often rumored to contain anything from animal urine to special oils, these were the guarded variables. It was a dance of fire and force passed only from master to apprentice, learned by hand and eye, not by book. The process was not just mechanical, it was alchemical. The smith wasn't just shaping metal, he was guiding an invisible transformation within its very structure, coaxing out a hidden potential that the Wootz steel contained. When that living chain of apprenticeship was severed, the entire intricate sequence vanished. All that remained were the finished swords, silent and magnificent, holding the answer in their blades but speaking in a language no one alive could understand. The recipe was lost, leaving modern science with a magnificent locked box and only the faintest idea of where to find the key. The silent swords finally found their voice in the 20th century. For the first time, science possessed the tools to interrogate these relics not as artifacts, but as complex material systems. Early metallurgists in the 1920s and 30s could confirm the basics, that Damascus steel was indeed a form of high-carbon steel. But this was like identifying the genre of a book without being able to read its pages. The composition was known, but the profound secret of its performance, the reason it behaved so differently from any other steel on Earth, remained locked away at a scale invisible to the human eye. The true nature of the mystery was molecular, and it would require a molecular witness to reveal it. That witness arrived with the Electron microscope, a device that allowed scientists to peer into the heart of the metal itself, to see the world the blacksmiths had shaped but never seen. This launched a new kind of quest led by researchers like Dr. John Verhoeven and Dr. Alfred Pendray. Their mission was not to make a modern copy, but to solve an ancient puzzle. They approached each historic blade as a detective would a cold case, treating every subtle clue in its microstructure as a silent testimony. Their work became a forensic investigation into the greatest technological disappearance in history. They were not merely studying metal, they were attempting to reconstruct a lost language from its scattered syllables, knowing that each clue they uncovered brought them closer to understanding how a medieval forge could achieve what modern factories could not. This sealed crucible was the true birthplace of the legend. Inside that simple clay pot, a quiet revolution took place. Iron ore, rich charcoal, and carefully selected leaves or wood chips were layered together, then heated for hours in a charcoal furnace. The crucible's lid was sealed shut, creating a miniature, self-contained world. This was not a roaring blast furnace, but a controlled, almost gentle process. The organic material did more than just burn. It transformed into carbon monoxide gas, which then seeped into the molten iron, bonding with it atom by atom. The genius was in the slow, deliberate cooling. Over many hours, sometimes even days, the melt solidified not all at once, but in a gradual dance of chemistry. This patient cooling allowed extraordinary structures to form within the steel. What emerged was the Wootz ingot, a lump of metal that looked unremarkable to the untrained eye, perhaps like a rough, metallic sponge cake. But to a master smith, this was the only canvas worth using. Its surface was sprinkled with bright, silvery specks like stars in a dark sky. These specks were particles of iron carbide, an incredibly hard compound of iron and carbon. They were suspended in a softer background of steel, creating a natural, pre-arranged pattern of hard and soft material right from the start. You can think of it like a block of marble to a sculptor. The veins and colors are already there, locked inside the stone. The sculptor's job is not to paint them on, but to carefully carve away everything that isn't the statue, to reveal the beauty that nature has already provided. In the same way, the Damascus smith did not create the pattern from nothing. His entire art was one of revelation. He took this Wootz ingot with its hidden landscape of carbide stars, and through heating, hammering, and folding, he gently coaxed that internal structure to the surface. Every strike of his hammer, every fold of the glowing metal, was a step in aligning and elongating those carbide particles, drawing them out into the flowing, watery lines that would become the blade's iconic signature. The ingot was the seed containing the entire genetic blueprint for the legendary sword. All the smith had to do was help it grow. The swirling pattern on the blade is where many modern assumptions go astray. For decades, even centuries, it was widely believed that Damascus steel was created the same way as the magnificent swords of the Vikings, through a technique called pattern welding. This method is a feat of physical artistry. A smith takes rods of different types of iron and steel, some high in carbon and some low, and heats them into a bundle. He then hammers, folds, and twists this bundle repeatedly, like kneading a metallic dough with contrasting colors. The result is a stunning, layered pattern etched into the surface by acid, revealing the different materials woven together. It is a mechanical mixing, a laminate of metals fused by sheer force and skill. And while pattern-welded swords are formidable works of art in their own right, they are fundamentally different from true Damascus steel. The Damascus pattern is not mixed in from the outside, it is grown from the inside. It is not a laminate but a birthmark. That iconic, watery design is not the result of twisting different metals together. It is the visible manifestation of a chemical process that occurred within a single, homogeneous piece of Wootz steel. The pattern is the surface expression of a hidden, three-dimensional landscape of microscopic structures. Understanding this distinction is the key that unlocks the real mystery. It shifts our focus from the smith's hammer to the silent, transformative events happening within the glowing metal itself. We are no longer looking at a crafted collage, but at a natural phenomenon being carefully guided to the surface. This means the secret was never in the folding technique alone, but in the precise thermal recipe that coaxed an intrinsic property into view. So if the pattern wasn't put there by folding different metals together, what exactly were the smiths doing with their hammers and fires, and what were they revealing? The hammer strikes were not just shaping metal, they were conducting a symphony of atoms. Each precise blow served a dual purpose, one visible and one invisible. To the eye, the smith was drawing a glowing ingot into the graceful curve of a blade, but within the steel, his hammer was performing a meticulous act of reorganization. The carbide particles, those hard, glittering specks from the Wootz, were originally scattered like gravel in soil. The force of forging began to break up their clumps and string them out, aligning them along the direction of the blade's length. This was not a random pounding, it was a guided flow, channeling the internal structure of the metal into a new, purposeful order. Yet the hammer alone could not create the legendary strength. Its power was unlocked only in partnership with the fire. After a session of hammering, the smith would return the steel to the forge, heating it to another specific, glowing temperature. This was not simply to soften it for more work. This heat cycle was a period of rest and recovery for the microstructure, a chance for the strained metal to relax and for new, even finer structures to begin precipitating out from the solid solution. Think of it like tending a garden. The hammering is the tilling of the soil, breaking up clumps and preparing the bed. The heat treatment is like the warm sunshine and quiet night that follows, allowing seeds to germinate and roots to establish themselves in the newly arranged earth. This dance, repeated over and over, heat, hammer, rest, is known today as thermal mechanical processing. It is a fundamental technique in modern metallurgy to create super-strong alloys for everything from jet engines to surgical implants. The Damascus smiths were practicing a primitive, intuitive form of this advanced science centuries before it had a name. They were manipulating the very fabric of their material through rhythm and temperature, setting a microscopic stage. With each cycle, the carbides were refined and redistributed, and the steel's internal landscape grew more complex and ordered. The smith, guided by tradition and the color of the glow, was unknowingly preparing the conditions for a phenomenon that would not be seen by human eyes for another 500 years. He was creating the perfect environment for nanotechnology to emerge spontaneously from the ancient forge. The final step was a baptism of fire and ice. After days of patient shaping, the glowing blade was plunged into its quenching bath. This was the most critical and dangerous moment in the entire process. The nature of this cooling fluid remains one of the great unanswered questions. Was it simple water, which cools with shocking speed and violence? Was it oil, which provides a gentler, more controlled hardening? Historical whispers speak of more exotic solutions, perhaps brine or even liquids containing organic materials. Each fluid cools at a radically different rate, and that rate dictates everything about the final steel's character. A quench that is too fast can make the metal incredibly hard but also brittle, causing the blade to shatter like glass under stress. A quench that is too slow leaves the metal soft and unable to hold a sharp edge. The master smith had to know, through experience passed down through generations, the exact recipe that would achieve the perfect balance. Some modern theories suggest the quenchant might have contained dissolved salts or plant extracts, introducing minute, purposeful impurities that subtly altered the steel's chemistry at the very moment of transformation. This final, violent thermal shock did more than just lock in hardness. It was the moment the blade's hidden soul became permanently visible. As the superheated steel met the cool liquid, the rapid contraction and crystallization etched the internal structure of aligned carbides into the surface, bringing the legendary watery pattern into stark, permanent relief. The quench was the point of no return. There was no going back, no second chance. In that instant of steam and sizzle, the smith's weeks of work, his intuition, and his guarded knowledge were tested. He would lift the blade from the bath, his breath held, examining the pattern that had emerged. It was the climax of his art, the moment an object of function was also crowned as an object of eternal beauty. The Electron microscope revealed a hidden universe within the steel. For the first time, researchers could see the bright, swirling lines of the Damascus pattern not as a simple decoration, but as a complex, three-dimensional structure. Those lines were composed of an incredibly hard compound called cementite, a form of iron carbide. But the true astonishment came when they looked closer, at a scale thousands of times smaller than the width of a human hair. The cementite bands were not solid slabs. Inside them, woven through the steel like the finest threads in a tapestry, were structures of breathtaking fineness. They were cementite nanowires. Imagine the hardest substance in the blade, not as a brittle sheet of glass, but as a bundle of flexible, ultra-strong cables, each one only a few atoms wide. This was the first concrete evidence of something extraordinary. The medieval smiths, through their patient cycles of heat and hammer, had not just made steel stronger. They had accidentally engineered a nanocomposite material. These nanowires acted like microscopic reinforcement bars, the same way rebar is embedded in concrete to prevent cracking. They gave the steel a combination of properties that seemed to defy logic. The blade could be both hard enough to hold a devastatingly sharp edge and flexible enough to absorb the shock of impact without shattering. The nanowires distributed stress throughout the metal, stopping cracks before they could spread. This nanotechnology was not added by the smith, it was grown by him. He created the perfect conditions of temperature, pressure, and time for these structures to self-assemble from the chemistry of the Wootz ingot. It was a discovery that rewrote the history of technology. The legendary sharpness of a Damascus sword was not just folklore, it was physics, engineered at the atomic level centuries before we knew atoms existed. But the story did not end with nanowires. The plot thickened even further in the early 2000s, when a team of researchers examined a 17th-century Damascus blade with a tool of almost unimaginable precision, a high-resolution transmission electron microscope. This device allowed them to peer into the atomic lattice of the steel itself. What they found was a landmark discovery that redefined the entire mystery. Nestled within the cementite bands, they identified carbon nanotubes. These are hollow cylinders of carbon atoms, mere billionths of a meter wide, arranged in a perfect hexagonal pattern. In the modern world, carbon nanotubes are considered a miracle material, among the strongest and stiffest substances ever discovered, with potential uses in everything from aerospace to medicine. Their presence in a 400-year-old sword was nothing short of astonishing. This was not just advanced metallurgy, it was a full-blown, functional nanotechnology. The implications were profound. It meant the legendary properties of the sword, its ability to be both razor-sharp and shock-absorbent, were not just aided by nanowires, but were fundamentally enabled by these carbon superstructures. The nanotubes would have acted like a microscopic skeleton within the steel, an internal reinforcement of unimaginable strength and flexibility. The blade was quite literally built from the atom up. But how could a medieval blacksmith, working with fire, hammer, and intuition, possibly create something that modern labs struggle to produce with perfect control? The answer lay not in his tools but in his ingredients. The team proposed a fascinating theory. The plant matter deliberately added to the Wootz crucible, leaves or wood from specific regions, was rich in trace impurities like vanadium. These elements did not just burn away, they became active participants in the chemistry. During the long, patient cycles of heating and forging in the smith's hands, these impurities acted as catalysts. They guided the self-assembly of carbon atoms, shepherding them into forming these perfect nanotube structures within the cooling steel. The smith, following an empirical recipe perfected over generations, was unknowingly setting the stage for a precise chemical reaction at the nanoscale. He was an inadvertent nanotechnologist, using the Earth's raw materials and the wisdom of tradition to build with atomic precision. His forge was, in effect, one of the world's first and most successful nanofactories. This revelation transforms our understanding of the craft completely. It was not magic, but a sublime intersection of material science, environmental knowledge, and perfected human technique, converging to create a material that the creators themselves could never fully comprehend. This changes everything we thought we knew about their craft. The master smith was not just a shaper of metal, he was an unwitting chemist, a curator of the Earth's hidden recipes. His most critical choice happened long before he ever lit his forge, in the selection of the raw Wootz ingot itself. He would have sought out metal from specific sources, passed along trade routes with a reputation for producing the best blades. He was selecting for a mystery he could not see. Modern analysis reveals that the legendary Wootz from mines in southern India and Sri Lanka contained a cocktail of trace elements: vanadium, molybdenum, chromium, and others. In contemporary steelmaking, these are often viewed as contaminants, carefully removed to create a pure, uniform product. But for Damascus steel, these impurities were the secret sauce. They were not flaws, they were features, essential ingredients in an ancient recipe. Think of it like baking bread. Flour and water alone make a simple, edible loaf. But add a pinch of salt, a touch of sugar, and most importantly, a live culture of yeast ingredients that seem insignificant by weight, and the dough transforms. It rises, develops complex flavors, and gains a structure it could never achieve on its own. Those trace elements in the Wootz were the yeast. They acted as catalysts and modifiers during the steel's long journey from molten ingot to finished sword. Vanadium, we now understand, played a starring role. This element is believed to be crucial for stabilizing the formation of those carbon nanotubes, acting like a microscopic scaffold that guides carbon atoms into their perfect hexagonal cylinders. It also helped control the size and spacing of the carbide bands, preventing them from clumping into brittle sheets and instead encouraging them to form the fine, dispersed structures that gave the blade its strength. The smith, by choosing an ingot from a specific region, was unknowingly selecting for a precise, complex alloy chemistry. His entire art, the rhythmic heating and folding, was a performance that only worked if the raw material contained this hidden symphony of elements. The land itself, the unique geology of those mines, was a silent partner in the process. This explains why the knowledge was so fragile, so impossible to reconstruct from the finished product alone. You could study 1,000 blades, but if you did not have the exact ore from those specific hills, you were missing the foundational note of the entire composition. The craft was not just a technique, it was a profound partnership between human skill and a very particular gift from the earth. This self-organization is a quiet miracle of physics. How could such intricate atomic architecture emerge without a blueprint or a guiding hand? The phenomenon is known as self-assembly, and it is nature's most elegant form of construction. Within the glowing Damascus steel, it was not a master engineer placing each carbon atom, but the atoms themselves following fundamental laws finding their perfect place. The specific chemistry of the Wootz ingot, rich in carbon and laced with those crucial trace elements, created a system brimming with potential. Then, the smith's patient thermal cycles, the precise heats, the controlled cools provided the rhythm. Each cycle was like a gentle shake to a box of mixed puzzle pieces. With every shake, the pieces jostle, and a few more snap into their correct positions, drawn together by the shape of their edges. In the steel, the driving force was not shape, but energy. Atoms, when given the chance through heat and time, will always seek the most stable, lowest energy arrangement possible. The trace impurities acted like social directors at this atomic dance, subtly influencing which partners came together and how they linked arms. Vanadium, for instance, preferred to bond with carbon in a specific way, effectively creating a template. As the steel slowly cooled from its forging heat, carbon atoms, guided by these templates, began to link up. They formed chains, then sheets, which then curled in on themselves into the seamless cylinders of carbon nanotubes. Simultaneously, iron and carbon assembled into the hard, needle-like crystals of cementite, with the nanotubes woven directly into their fabric. The smith's true genius was environmental. He did not build the nanostructures, he cultivated them. His forge was a garden, and his carefully managed heat was the climate. He knew, through generations of trial and error, that if he maintained this specific thermal rhythm, so many heats to this particular color, so many hammer strokes, a quench at this exact moment, the steel would reliably bloom with its legendary pattern and properties. He was orchestrating a natural process he could not see, trusting that the laws of physics, when provided with the right ingredients and conditions, would produce the desired result every time. This is the sublime intersection where human intention meets natural law. The smith provided the question written in fire and iron, and the atoms, following their ancient rules, whispered back the answer in a language of perfect, invisible geometry. That final etching reveals the invisible. When the master smith polished his finished blade and applied a mild acidic solution, often a simple citrus juice or fermented grain, he was not adding color, he was uncovering a truth. The acid reacted with the different zones of the steel at different speeds. The bands rich in hard carbides and nanotubes resisted the bite of the acid, remaining smooth, polished, and reflective. The softer, purer steel between them was more vulnerable, etching away faster to become a matte, dark gray. This contrast is what brings the legendary Damask Pattern, also known as the watering, into breathtaking visibility. The swirls and waves you see are not painted on. They are a literal, three-dimensional relief map of the blade's internal architecture. Every curve in that pattern corresponds directly to the flow and alignment of the carbide bands within the metal, bands that were painstakingly arranged by the hammer and guided by the heat. It is a macro view of a nano-world. Think of it like looking at a satellite image of a mountain range. From high above, you see the sweeping ridges and deep valleys, the way the land folds and flows. That majestic view is created by the underlying geology, the immense tectonic forces that shaped the stone over eons. The Damask Pattern is that satellite view. The swirling lines are the surface expression of the immense, hidden landscape of nanostructures beneath. Each blade's pattern is utterly unique, a frozen fingerprint of its creation. It records the exact number of folds, the specific angles of the hammer strikes, the precise temperatures reached and for how long. No two swords could ever have the same pattern because no two forging sessions were perfectly identical. The damask is therefore far more than beautiful decoration. It is a diagnostic report. It tells the story of the blade's making, a visual transcript of the ancient recipe followed by the smith. A tight, delicate pattern suggests a different thermal history than a bold, sweeping one. In this way, the sword carries its own biography written in light and shadow upon its skin. It is the final, beautiful proof that the legend was not forged in myth, but in the silent, self-assembling dance of atoms, made visible for all to see. The legend of the Damascus sword is now grounded in physics. Its phenomenal reputation was not just marketing, but a direct result of that hidden nanostructure, which delivered three distinct and measurable performance advantages. The first was a masterful balance of hardness and toughness, two properties that are usually at odds in metallurgy. A blade that is extremely hard can hold a razor edge, but it becomes brittle, prone to snapping under a heavy blow. A blade that is very tough can bend and absorb impact, but its edge will quickly roll and dull. Damascus steel achieved both. The hard cementite bands, reinforced with carbon nanotubes, provided the relentless sharpness. Meanwhile, the softer, purer steel matrix surrounding them acted as a flexible sheath, giving the blade the resilience to withstand brutal combat without catastrophic failure. It was a symbiotic relationship engineered at the atomic level. The second advantage was an invisible defense system. In any material, stress and impact can create microscopic cracks. In ordinary steel, these cracks can propagate freely, growing until the blade breaks. In Damascus steel, the nanostructures acted as a network of crack arresters. Imagine a crack like a tiny tear starting to spread through the metal. When it encounters a band of cementite nanowires or, more importantly, a carbon nanotube, its path is blocked. The incredibly strong nanotube either stops the crack entirely or forces it to change direction, diverting its energy and preventing it from growing into a critical flaw. This made the blade remarkably durable and fatigue-resistant, capable of surviving the repeated stresses of battle that would destroy lesser weapons. The third advantage borders on the magical but has a logical explanation. Some researchers have proposed that the unique composite structure allowed for a form of self-sharpening. As the blade was used, the softer steel matrix between the ultra-hard carbide bands would wear down very slightly faster. This could cause microscopic fragments of the matrix to break away during cutting or honing, continually exposing fresh, sharp carbide edges beneath. It would not be an automatic process, but it meant that with use and proper maintenance, the sword could retain a viciously effective cutting edge longer than a uniform piece of steel. So when historical accounts speak of these swords slicing a floating silk scarf or cleaving through an opponent's armor, they are not describing fantasy. They are reporting the observed effects of a material that was, by medieval standards, almost supernatural. The myth had a solid, nanostructured foundation. Superiority was not a guarantee of survival. By the middle of the 18th century, the creation of true Damascus swords, the kind with the self-assembled nanostructures, simply stopped. The last masters passed away and the forges fell silent. This was not the failure of a flawed technology, but the quiet collapse of an ecosystem. Several converging pressures, each one manageable on its own, came together to snuff out a flame that had burned for 1,000 years. The first pressure came from the earth itself. The specific mines in India and Sri Lanka that produced the magical Wootz ore, rich in vanadium and other crucial catalysts, were not infinite. Historical records and geological surveys suggest these high-quality surface deposits may have been exhausted through centuries of extraction. Think of it like a vineyard that produced a legendary wine from a unique soil. Once that particular plot of land is spent, you can still grow grapes elsewhere, but the distinct flavor, the essence of the vintage, is gone forever. Without that exact geological recipe, the seed of the process was lost. Smiths could no longer source the raw material that made their art possible. They might have tried with other ores, but the resulting steel would have lacked the hidden architecture, producing a blade that was merely a beautiful imitation, missing its legendary soul. The second pressure was a tidal wave of change in warfare and industry. The 18th century saw the rapid rise of reliable, mass-produced firearms. The economics were brutal. A regiment could be equipped with dozens of muskets in the time, and for the cost it took a single master smith to produce one supreme sword. The role of the elite warrior, whose skill was magnified by a transcendent weapon, was being eclipsed by the disciplined volley of common infantry. At the same time, new methods for producing uniform cast steel were being developed in Europe, promising consistency and scale. The world's demand was shifting from unique masterpieces to reliable, interchangeable parts. The Damascus craft, a slow, expensive, and deeply personal art, could not compete in this new economy of volume and speed. It became a luxury item in a world that was starting to value utility. But perhaps the most fragile element was the knowledge itself. This was not a science written in textbooks with formulas and tolerances. It was a living craft, an oral and tactile tradition passed directly from a master's hands to an apprentice's eyes. The full ritual, the feel of the right heat, the sound of the hammer on the specific steel, the instinct for the quencher, was stored in human memory and muscle. This chain was terrifyingly easy to break. A master could pass without a worthy apprentice. A political conflict or economic hardship could scatter a community of smiths. A single generation of interrupted teaching was all it took to sever a lineage that stretched back centuries. And because the smiths worked from empirical success, not theoretical understanding, they were guardians of a process whose deepest principles were invisible to them. They knew that if you did steps A, B, and C in this exact order with this specific ore, you would get a magnificent sword. But they did not fundamentally understand why trace vanadium was essential, or how the cooling rate catalyzed nanotube growth. So when the perfect ore vanished, they had no framework to adjust. They could not reverse engineer a solution because they never knew the core equation. The craft was a peak reached by an ancient path. When that path was washed away by the rains of change, there was no map to find it again. The technology did not become obsolete because something better came along. In many ways, nothing better ever did. It vanished because the unique, delicate conditions that allowed it to exist, the specific ore, the patient economy, the unbroken chain of touch, all dissolved at once. It was a perfect storm of loss, leaving behind only echoes in steel and a mystery that would taunt the modern age for centuries. The silence of history was finally broken in a university laboratory. While scientists had peered into the steel's secret heart, two researchers, John Verhoeven and Alfred Pendray, embarked on a more ambitious quest. They were not content to merely understand the sword. They wanted to rebuild it from the ground up. Their work became a modern alchemy project, a deliberate attempt to resurrect a ghost. For years, they studied the clues left in antique blades, not as historians but as forensic engineers. They knew the final composition. They had seen the nanowires and nanotubes, so the question shifted from what it was to how you could possibly make it happen again. Their process was a beautiful inversion of the ancient craft, where the medieval smith started with a mysterious ore and an empirical ritual. Verhoeven and Pendray started with a clean slate of pure, modern materials and the full weight of contemporary science. They began with high-purity iron and carbon, the basic building blocks. Then, critically, they added back in the secret ingredients. Knowing from their analysis that trace elements like vanadium were key, they introduced them with laboratory precision, in amounts measured to the fraction of a percent. This was the first major revelation of their recreation. It proved that those impurities were not accidental contaminants, but deliberate, necessary components of the recipe. The next challenge was the rhythm. They had to mimic the thermal dance of the ancient forge without any living master to guide them. They designed precise heating cycles, holding the steel at specific temperatures for exact periods of time, then cooling it in controlled stages. Their hammer was not a hand tool but a hydraulic press, applying measured, repeatable pressure. They were, in essence, writing a sheet of music for an orchestra of atoms, note by note, based on the faint echoes of a performance no one had seen for centuries. And then, one day, they succeeded. The steel bloomed with the flowing, watery damask pattern. More importantly, under the electron microscope, it revealed the holy grail, the cementite nanowires, and nestled within them the carbon nanotubes. This was a monumental moment. It transformed the lost art from a myth into a reproducible scientific discipline. It proved conclusively that the legends were not exaggerations, but reports of a real, achievable material phenomenon. The process was no longer a black box of mystery, it was a deciphered code. Yet, this scientific triumph came with a profound and humbling caveat. The laboratory recreation proved the legend was real, but it also revealed a deeper truth about progress. For centuries, we assumed that technological advancement was a straight line, moving from primitive to sophisticated. The story of Damascus Steel shatters that assumption. It shows us that a civilization can reach a technological peak by one path, lose it completely, and then have a future civilization, armed with entirely different tools, struggle to climb back to that same height. This isn't just about swords, it's about a fundamental shift in how we think about making things. The modern world builds from the top down. We design with computer models, we fabricate in sterile environments, we assemble with microscopic precision. We impose order from the outside in. The Damascus smiths worked from the bottom up. They didn't build the nanostructures, they created the conditions for the nanostructures to build themselves. They provided the recipe and the rhythm, and the material did the rest. This ancient approach, this partnership with natural self-assembly, is now one of the most exciting frontiers in modern materials science. Researchers are looking at the principles behind that Wootz steel and asking a revolutionary question. What if we could design alloys that, like Damascus steel, grow their own internal reinforcement? Instead of painstakingly embedding fibers or particles, we could code the chemistry and the heat treatment so that the perfect strengthening structures simply emerge during manufacturing. This could lead to a new generation of materials. Imagine an aircraft alloy that develops its own network of nanotubes during forging, becoming lighter and stronger than anything bolted together. Think of a biomedical implant like a hip replacement that isn't just biocompatible, but actually encourages the growth of bone into its nano-textured surface, locking it securely into the body through natural processes. The Damascus sword is a 1,000-year-old proof of concept. It shows that incredibly sophisticated nanomaterials can be created without a single electron microscope or clean room. They can be forged in fire, shaped by a hammer, and grown through patience. This bridges a profound gap between ancient empirical wisdom and 21st century ambition. It teaches us that sometimes the most advanced solution isn't to force nature into submission with ever more complex tools, but to understand its rules so deeply that we can invite it to collaborate. The smiths of Damascus didn't know they were nanotechnologists, but their legacy is now guiding the scientists who are. The comparison is irresistible, a duel of legends across continents. On one side, the Damascus sword with its watery, organic pattern. On the other, the Japanese katana with its sleek, deadly curve and legendary sharpness. Both are icons, the absolute pinnacle of their respective worlds, yet they achieve their mythical status through completely different philosophies of creation. Understanding this distinction takes us to the very heart of what makes each blade unique. The katana is a triumph of mechanical perfection. Its journey begins with Tamahagane steel, produced in a traditional clay furnace called a tatara. This steel is rich in carbon but also contains impurities like slag. The smith's first act is one of purification. He heats the steel and hammers it flat, then folds it back onto itself, welding the layers together. He repeats this folding process over and over, sometimes more than a dozen times. Each fold doubles the layers, multiplying them into the thousands. This relentless mechanical work serves a clear purpose. It literally kneads the impurities out of the metal, distributing the carbon evenly and creating a laminated structure of astonishing uniformity. The true magic, however, happens in the quenching. The smith paints the blade with a special clay slurry, applying a thin layer along the razor's edge and a thick layer along the spine and sides. When the glowing blade is plunged into water, the thinly coated edge cools with shocking speed, transforming into an incredibly hard, crystalline form called martensite. The thickly coated spine cools much more slowly, remaining a softer, more flexible steel. This single, brilliant process, known as differential hardening, creates a blade that is a study in controlled contradiction. It possesses a hard, brittle edge capable of legendary sharpness, backed by a soft, shock-absorbing spine that prevents it from snapping. The visible line between these two zones, called the hamon, is the katana's signature, a frozen record of that moment of thermal violence. The katana's strength is architectural, a masterpiece of macroscopic engineering built through sheer force, meticulous layering, and a perfectly controlled thermal gradient. It is the ultimate refinement of the material given to the smith. The Damascus sword follows a different logic entirely. Its strength is not built layer by layer, but grown from within. There is no differential hardening, no clay coating. The smith starts with a single, homogeneous ingot of Wootz steel, a material already pre-loaded with its secret recipe. His folding is not to purify or laminate, but to gently guide and elongate the internal carbide structures that already exist. The quenching is uniform, hardening the entire blade as one. The Damascus pattern is not a hamon, a line between two different zones. It is the surface expression of a three-dimensional, self-assembled nanostructure that permeates the entire blade. Its legendary properties, the blend of hardness and toughness, come not from combining different types of steel, but from a single steel that has been coaxed into organizing itself at the atomic level. One tradition is a symphony of force and control, removing imperfection to achieve purity. The other is a symphony of chemistry and patience, using imperfection, those trace elements, as the essential catalyst for growth. The katana is a sculpture carved from a block. The Damascus blade is a crystal garden cultivated from a seed. Both are sublime achievements, but they speak in different languages about the relationship between human will and the hidden potential of the material world. Across the cold northern seas, another legend was being forged in fire. The Viking Ulfberht swords, bearing that distinctive inlaid name, were the terror of their age. Crafted between the 9th and 11th centuries, these weapons were so far ahead of their time that finding one was like discovering a smartphone in a 19th century farmhouse. Like the Damascus blades, they were born from high-carbon crucible steel, a material that had to journey thousands of miles from production centers in Central Asia, likely along the river trade routes through the lands of the Rus. This steel gave the Ulfberht its remarkable purity and strength, setting it apart from the brittle, slag-ridden iron common in Europe. A warrior wielding an Ulfberht held not just a weapon, but a technological advantage as decisive as the Damascus sword was in the Middle East. Yet the two masterpieces, while cousins in quality, were strangers in their making. The Ulfberht's secret lay in achieving a new kind of uniformity. Its crucible process aimed to remove impurities, creating a more homogeneous steel blank. The smith would then expertly work this blank, carefully controlling its carbon content through forging to create a resilient, deadly sharp blade that could flex and return true. Its power was in its consistency, a monolithic strength without the complex internal patterning. There was no self-assembled nanotechnology within its core, no watery damask gracing its surface. Its signature was simply its name, Ulfberht, spelled out in iron letters, a brand of supreme quality in an age of crude imitations. This presents us with a stunning reality. In the same centuries, separated by continents and cultures, human ingenuity was climbing the same mountain by entirely different paths. The smiths of the Rhine, working with imported Eastern steel, pursued perfection through purity and expert physical manipulation. The smiths of Damascus, working with a different Eastern steel, pursued perfection by cultivating complexity and guiding natural self-organization. Both reached a peak that their contemporaries could not comprehend. This tells us that the ancient world was not a place of uniform technological stagnation. It was a landscape dotted with isolated, brilliant fires of advancement, each burning with its own fuel and casting its own unique light. The Ulfberht and the Damascus sword were not competitors. They were parallel answers to the same eternal question: how can we take the gifts of the earth and forge them into something transcendent? One answered with the clean line of the master's chisel, the other with the cultivated bloom of a hidden garden. Both answers were, for their time, nothing short of miraculous. But unlocking these secrets comes at a delicate cost. To truly understand the sword's internal magic, science needed to look inside, and that meant cutting into history itself. This creates a profound ethical tension, a modern conflict between the drive for knowledge and the duty of preservation. Museums and private collectors are the guardians of these irreplaceable artifacts, each blade a singular chapter in the story of human ingenuity. For centuries, their role was purely custodial, to protect and display. Then came the Electron microscope and its demand for a physical sample. Imagine a curator faced with a heartbreaking request from a researcher to allow a tiny sliver, perhaps just a millimeter wide, to be removed from the edge of a priceless 17th century sword. It is an act of destruction, however minute. That fleck of metal is gone forever, altering the artifact in a permanent, if nearly invisible, way. The argument against it is powerful and emotional. These objects have survived battles, time, and neglect. They are not just data points, they are cultural treasures, and our generation does not own them outright. We hold them in trust for the future. To damage one, even for science, can feel like a violation of that sacred trust. Yet the argument for analysis carries its own compelling weight. A sword sitting untouched in a glass case is a silent mystery. The sample, once taken, can be studied not just today, but for decades to come, as new analytical tools are invented. That tiny fragment could contain the blueprint for materials that change our world, inspiring stronger, lighter alloys or new medical implants. The knowledge gained is not just academic, it is potentially transformative. Is the loss of a microscopic piece from one artifact justified if it helps resurrect an entire lost technology for the benefit of all? There is no easy answer, and this ethical balancing act has forced innovation in how we study the past. To minimize harm, scientists have pioneered remarkable non-invasive techniques. Advanced X-ray fluorescence can map the elemental composition of the blade's surface without touching it. High-resolution computed tomography scans, like those used in hospitals, can create three-dimensional models of the internal structure, revealing density variations that hint at the carbide bands. These methods are the archaeology of the future, allowing us to see through time without leaving a mark. The debate itself is a quiet subplot in the sword's long journey. It reflects a shift in how we value our heritage. We no longer see these objects merely as beautiful relics, but as complex documents, holding encrypted information about our ancestors' intelligence. Each decision to sample or not to sample is a negotiation between two forms of respect: respect for the physical object's integrity and respect for the intellectual achievement it represents. This tension ensures that every new discovery about Damascus steel is considered carefully, its cost weighed against its potential to illuminate not only the past but also the path forward. The swords, having survived the forge and the battlefield, now find themselves at the center of a thoughtful conversation about what we owe to history and what history might still owe to us. The true power of a Damascus sword was never measured by the edge alone. Its value extended far beyond the battlefield, woven deeply into the cultural and spiritual identity of the societies that created it. In the Islamic world, the blade was more than a weapon. It was a symbol of profound virtues. It represented divine justice, a swift and decisive force for righteousness. It embodied the strength of faith and the favor of God, a tangible blessing for the warrior who wielded it with honor. This is why so many of these swords are adorned with exquisite calligraphy, their surfaces inscribed not with the names of kings but with prayers, verses from the Quran, and blessings for the bearer. The steel itself became a sacred text, a physical object carrying spiritual weight into combat. The warrior carried not just a tool but a covenant. This transformation from instrument to icon speaks to a world view where the material and the spiritual were inseparable. The legendary pattern on the blade, that watery, organic damask, was not seen as a mere accident of metallurgy. To the artistic and philosophical mind of the era, it was a direct reflection of the divine beauty inherent in the natural world. It echoed the flow of rivers, the grain in wood, the patterns in stone, all seen as manifestations of a single creative force. The sword's beauty was evidence of a deeper cosmic order, a unity between the craft of human hands and the underlying principles of creation. This cultural dimension completes our understanding of the sword's legacy. It reminds us that a technology, no matter how advanced, never exists in a sterile, practical vacuum. It is born into a world of meaning. The Damascus blade was a nexus point where supreme material science met high art and where both were elevated by spiritual significance. It was a physical philosophy, the very act of its creation, a patient guiding of inner nature to reveal hidden beauty, mirrored a spiritual pursuit, the refinement of the self to reveal inner virtue. To hold such a sword was to hold a piece of that philosophy, a reminder that true strength is a harmony of the hard and the flexible, the sharp and the resilient, the earthly material and the eternal idea. The sword's final lesson is not about how to cut, but about what we choose to value. It tells us that our greatest creations are those that serve both the hand and the heart, that solve a physical need while simultaneously speaking to the human spirit's endless search for meaning and connection. Yet with such a powerful legacy comes a cloud of modern confusion. We need to separate the timeless truth from the common misconceptions that have grown around it. First, let's be clear, a Damascus sword is not magically superior to every piece of modern steel. Today's metallurgists, with their controlled laboratories and periodic table of alloying elements, can create steels that outperform the ancient blades in specific, measured ways. A modern tool steel might hold an edge longer under laboratory wear tests, and a specialized aerospace alloy can withstand stresses and temperatures the medieval smiths could never have conceived. The genius of Damascus steel was not in being the absolute hardest or the absolute toughest material possible. Its true achievement was reaching that breathtaking balance of hardness, toughness, and resilience using nothing but earth, fire, and human intuition. It was a masterpiece created with a pre-industrial toolkit, a solution that emerged from the constraints of its time, not in spite of them. This distinction matters because it shifts our awe from a blind belief in supernatural metal to a profound respect for ancient ingenuity. They worked with what they had, and what they achieved with it remains astonishing. A second, widespread myth involves the blade's iconic beauty. You cannot fake the Damask pattern with a simple surface etch. That watery design is not a tattoo applied to the skin of the metal. It is the visible grain of the steel itself, running through the entire thickness of the blade. If you were to cut a true Damascus blade in half and polish the cross-section, you would see the pattern continuing all the way through, like the rings in a tree trunk. This is because the pattern is the physical manifestation of the carbide bands, the nanostructures that define the material from its core to its surface. A surface etching on a uniform piece of steel can create a decorative design, but it will be shallow, a mere skin-deep imitation. It lacks the depth and the three-dimensional reality of the genuine article. The true damask is a structural signature, not a decorative afterthought. This leads directly to the most common point of confusion in the modern marketplace. Walk into many knife shops or browse online today, and you will find countless blades labeled as Damascus. The vast majority of these are beautiful, high-quality knives, but they are not made using the ancient Wootz method. They are what is properly called pattern-welded steel. Modern smiths take layers of different alloys, often high-carbon and nickel stainless steels, and forge-weld them together, then twist and manipulate the billet to create stunning, often dramatic patterns. When etched, the different metals react to create striking contrasts. This is a legitimate and skilled craft in its own right, but it is a mechanical lamination, not the cultivation of a self-assembling nanostructure. To avoid diluting the historical term, these are often sold as Damascus pattern steel, a nod to the aesthetic inspiration rather than the technological lineage. The commercial use of the name is understandable, the visual resemblance is strong, and the word Damascus carries immense prestige. But for those who now understand the hidden world within the original blades, the difference is fundamental. One is a painting of a mountain range, the other is an actual slice of the mountain itself, complete with all its internal geology. Recognizing this distinction does not diminish the value of modern pattern-welded knives, but it does protect the legacy of the genuine article. It ensures that when we speak of a Damascus sword, we are referring to that specific, almost alchemical convergence of unique ore, guided self-assembly, and a lost chapter in humanity's long conversation with the material world. The real thing was not just a product, it was a phenomenon. The legacy of Damascus steel now lives in two distinct worlds, one of priceless preservation and another of passionate revival. Authentic antique swords have long since left the realm of commerce to become crown jewels of museum collections and the ultimate, often unattainable, prize for serious collectors. When one does surface at a prestigious auction, the price can reach into the hundreds of thousands, even millions of dollars, a figure that reflects not just the object's beauty, but its status as a singular artifact from a lost technological age. Owning one is less about possession and more about becoming a temporary guardian of history itself. This immense value and scarcity have naturally ignited a vibrant market for modern interpretations, where the spirit of the Damascus blade is reborn through contemporary hands. Here, the line between replica and homage becomes beautifully blurred. On one end of the spectrum are master bladesmiths who have studied the published work of researchers like Verhoeven and Pendray. They begin with pure materials, carefully introducing trace elements to mimic the catalytic effect of the original Wootz. Through patient thermal cycling, they coax out a genuine damask pattern grown from within the steel, creating what is often called neo-Wootz. These blades are not historical replicas in the strictest sense, as the exact ore chemistry is forever lost, but they are legitimate descendants, achieving similar nanostructures and performance through scientific understanding rather than inherited ritual. They are experiments in resurrection, each one a testament to the decoded secrets of the ancients. More commonly, the market flourishes with stunning pattern-welded blades, proudly labeled as Damascus. Artisans layer and twist different steels, creating breathtaking, intricate mosaics that pay visual tribute to the flowing patterns of the originals. While the internal mechanism is different, the skill involved is extraordinary. and the resulting knives are functional works of art celebrated for their own merits. For the modern enthusiast, this entire spectrum offers a profound connection. Whether it is acquiring a Wootz blade where science has reclaimed a ghost of the old magic, or a masterfully crafted pattern-welded piece that captures the aesthetic soul of the tradition, the act of ownership changes. It becomes a way to hold a piece of this enduring mystery, to feel the balance of a blade that echoes an ancient dialogue between fire, earth, and human ingenuity. These modern creations answer a deep-seated yearning not just for a tool, but for a tangible link to a story of forgotten brilliance, allowing the legend to live on not only behind glass but in the hand. Even with the nanowires and nanotubes mapped, the ancient forge still holds its cards close. The exact nature of the quenching fluid, the final, decisive ingredient, remains a historical ghost. Was it water from a specific well, rich in minerals? Was it oil infused with organic compounds, as some fragmented texts suggest? This missing piece is more than a trivial detail. It is the final variable in a 1,000-year-old equation. The rate and nature of that cooling shock did not just harden the steel, it locked the nanostructures into their final, perfect alignment. Without knowing the exact medium, we cannot perfectly replicate the ritual, only approximate its outcome. And then there is the silent chemistry of the trace elements. We know vanadium was crucial, but what of the others? Molybdenum, chromium, perhaps even arsenic from certain ores. Their precise roles are not fully mapped. Did they work in concert, a microscopic council guiding the growth of different structures at different stages of the heating cycles? Or were some merely passengers incidental to the process? The interactions within that glowing metal were a complex dance, and we have only identified a few of the dancers. This uncertainty is not a failure of science but an invitation. It means the investigation is far from over. The next phase of discovery will employ tools that sound like science fiction. Atom probe tomography, for instance, allows scientists to reconstruct a material's structure atom by atom, building a three-dimensional map of its elemental composition. Applying this to a sliver of genuine Damascus steel could reveal the exact location and chemical state of every trace element, showing us not just what was there, but what it was doing at the moment the blade was quenched. Could such analysis reveal even more advanced, unseen nanostructures, perhaps different forms of carbon we have not yet detected? The possibility is electrifying. Each new tool is like a stronger lens turned on an old masterpiece, revealing brushstrokes and layers of paint previously invisible. But the most profound questions now look forward, not back. The principles we have uncovered, this bottom-up approach of guided self-assembly, are a new design philosophy for the modern world. What if we could create Damascus-inspired materials for entirely new purposes? Imagine a structural beam for a skyscraper that develops internal nanotube reinforcement as it cures, becoming lighter and stronger than any steel truss. Envision a biodegradable medical stent implanted in an artery that slowly dissolves in the body while encouraging healthy tissue to grow into a nanostructured pattern it leaves behind. The ancient craft points toward a future where materials are not just assembled, but grown to order with their functionality encoded in their chemistry and their response to heat. The story of the Damascus sword, therefore, refuses to end in a museum display case. It has jumped the gap from history to materials science, from legend to laboratory inspiration. Every answer it has given us about the past has opened a new, more refined question about the future. The swords are no longer silent relics. They have become active collaborators in a conversation that spans a millennium, whispering not just how they were made, but how we might build our world anew. This tale of Damascus steel reveals a profound truth about human progress. Our ingenuity has often sprinted far ahead of our understanding, leaving behind artifacts that are both puzzles and prophecies. Those medieval blacksmiths, guided by the glow of the forge and the wisdom of their hands, were practicing a science they could not name. They were nanotechnologists 5 centuries before the word existed, their greatest achievement a form of material magic they themselves could never fully explain. They crafted objects designed for conflict that somehow transcended their purpose, becoming enduring symbols of art, culture, and the relentless human drive to perfect the world around them. Solving this historical mystery does more than satisfy our curiosity. It forges a vital bridge. On one side stands the empirical wisdom of the past, knowledge earned through generations of trial, error, and careful observation. On the other stands the analytical power of the present, with its electron microscopes and atomic probes. By bringing these two worlds into conversation, we accomplish something remarkable. We validate the genius of our ancestors not as myth, but as measurable fact, while simultaneously gaining a new design philosophy for our own future. So the next time you see that iconic, watery pattern swirling across a blade, see it for what it truly is. It is not merely a decoration. It is a topographic map of a hidden, microscopic landscape. It is the visible signature of carbon nanotubes and self-assembled wonder, a permanent inscription left by masters who worked in fire and faith. It is, above all, a timeless testament to the beauty that emerges when human patience meets the silent, perfect laws of the natural world.